Hello, learners. Welcome to our new session. This is Mohamed Ashiq PM, PG Department of Economics, Safa College of Arts and Science, Pukatri. Our new topic, constraint optimization with Lagrange multiplier. This topic is related with the QT or quantitative method. This is for finding constraint maximization or minimization. The constraints means in the case of profit maximization, there are so many constraints. In this session, we deals with the constraint optimization with the Lagrange multiplier. Okay, the Lagrange multiplier invented in the year 1797 by Joseph Louis Lagrange. Okay, the Lagrange multiplier denoted by lambda, letter lambda. The examples are profit maximization, utility maximization, or cost minimization, etc. There are maximization or minimization in this session. Okay, we want to know the maximization or minimization values. So we want to Lagrange multiplier with the steps. The steps are majorly 5 steps included in this method. The first step is set the constraint equal to 0, constraint equation equal to 0, then find a new functional form v. Okay, then second step is take all the partial derivatives. We want to find out all partial derivatives equal to 0, make it. Okay, then third step is find the variable values, and the lambda value. Then the fourth step is substitute the values to the new function form v. Okay, then the last step is that use the second order partial derivative, second order condition for identifying maximum or minimum for the use of bordered Hessian tool or method. Okay, so we can go through the steps with an example. The example is that optimize z is equal to, the example question is optimize z is equal to x square plus y square subject to constraint y is equal to 10 minus x. Here z is equal to x square plus y square is a objective function, and the constraint function is y is equal to 10 minus x. The objective function is maybe profit maximization or cost minimization or utility maximization, anything will. Okay, then we can go through the steps. First step, you know that constraint equal to 0. You want to make constraint equal to 0. Then the constraint equation is y is equal to 10 minus x. The equation want to equal to 0. Okay, then the y value will move to the right part of the equation. Then the equation will be 10 minus x minus y is equal to 0. Okay, then we want to create a new function v. The new function created by multiplying Lagrange multiplier lambda with the constraint equation and the equation added to the objective function, that is v is equal to x square plus y square plus lambda into 10 minus x minus y. When we multiply with lambda, it will be v is equal to x square plus y square plus 10 lambda minus x lambda minus y lambda. This is the new function v. Okay. Then the step 2, take all the partial derivatives. Okay. Take all the derivatives equal to 0. Then the first derivative is dou v by dou x. Dou v by dou x is equal to 2x minus lambda is equal to 0. That is x square. When we partial derivative with x, then we consider only x parts. Okay. Then the x parts x square. X square will be 2x, become 2x, and x lambda minus x lambda become minus lambda, then 2x minus lambda. Okay. We want to make it equal to 0. So, 2x minus lambda is equal to 0. Same way, the second equation will be created. Dou v by dou y is equal to 2y minus lambda is equal to 0. And the third equation is dou v by dou lambda, the partial derivation of v with the lambda. Okay. Then this is equal to 10 minus x minus y is equal to 0. We take all the partial derivatives. Then the next step is that, third step is that, find out all the variable values and the lambda value. In the equation 1, 2x minus lambda is equal to 0. 2x minus lambda is equal to 0. Then we, next value, that is when lambda is moved to the right part of the equation 1, then we can get 2x equal to lambda. Same way we can do with the equation 2. Then 2y minus lambda is equal to 0. It will become 2y is equal to lambda. So, lambda is equal to 2x also equal to 2y. Okay. Then the combining these equations, we can get 2x equal to 2y. 2x equal to 2y. Then the 2 will be moved to the right part of the equation. Then x equal to 2y by 2. 2y by 2. Then we can delete the 2 with the 2. Then x equal to y. X is equal to y. We can get x equal to y. Then equation 3. We can use equation 3. Substitute the y value. Substitute the y value in the equation 3. Then we can get 10 minus x minus x. Y substitute with the x. Okay. At 10 minus x equal to 0. Then x minus x is equal to minus 2. So, 10 minus 2x equal to 0. Minus x is equal to minus 2x. So, we can write 10 minus 2x equal to 0. Then minus 2x is equal to minus 10. It will come 10 move to right part of the equation, then minus 2x equal to minus 10. In both side of the equation have minus value. So, we can delete the minus. Then 2x equal to 10. Then 2 will move to right part of the equation. Then x equal to 10 by 2. Then x equal to 10 by 2 is 5. Then x equal to 5. So, y is also equal to 5 because x equal to y. So, when x equal to 5, then y is also equal to 5. Then we can find the lambda value. Lambda is equal to 2x or 2y. We can use any equation. Okay. Then lambda is equal to 2 into 5 is equal to 10. So, we find the all variable values and lambda value. Variable values are x equal to 5 and y is equal to 5. Then lambda value is 10. Okay. Then the step 4, substitute the value to the function v. We want to substitute the values of the variable and lambda to the new function v. Then we can get v is equal to 5 square plus 10 into 10 minus 5 minus 5. It will become is equal to 50. V is equal to 50. So the optimized value is 50. So the optimized value or minimized or maximized value is 50. Okay. Then the speciality of lambda value. We want to know the speciality of the lambda value. When our constrained value changes, then we can find out the optimized value easily. It is because of the lambda value speciality. Okay. When our constraint value y is equal to 10 minus x it is our initial constraint value, y is equal to 10 minus x. It will become changed to y is equal to 11 minus x. 10 changed to 11. Okay. Y is equal to 11 minus x. Plus 1 value is changed. Plus 1 value is changed. So we want to find the optimized value by the use of lambda. Plus 1 into lambda value. Plus 1 is 1 into lambda value is 10. So 1 into 10, 10. Then 10 plus 50. 50 plus 10 is equal to 60. The 60 is the optimized value. Okay. In another example is that when the constraint equation changed to y is equal to 12 minus x, there plus 2 value is changed. So plus 2 into lambda, plus 2 into lambda, plus 2 into 10 is equal to 20. The 20 will be added with the initial optimized value 50. Then we will get the 70 is the optimized, new optimized value. It will helpful for all sessions, all businessman or any constraint optimization user, researchers or students, all. Everyone can use this specialty of lambda for reducing their time for, okay. Then the last step is that, okay, use a second order condition for identifying the value is maximum or minimum. We find in the fourth step, we find out the optimized value, but we don't know about this value is maximization value or minimization value. For the identification of this problem, we need to use a method or tool, that is bordered Hessian tool. This is a second order condition for identifying value is maximum or minimum. This is a sufficient condition for optimization method. This is a sufficient condition and it is a matrix form. The bordered Hessian tool method is a matrix form and Hessian value is determined by value of Hessian matrix. Okay. The value is determined, the value is decided, the optimized value is maximum or minimum when the Hessian value is greater than 0, that is positive. Okay, Hessian value is greater than 0, is positive, then there is minimization. Okay, when the Hessian value is less than 0, that means less than 0 means negative value. Okay, when it's negative value, Hessian value is negative, then the function is maximization. Okay, this is all in the part of Lagrange multiplier. We need so many points for finding the bordered Hessian tool. It will include in the next session. Okay, I will conclude my session. Thank you so much.